If you tell a computer program to, pause for 1 second, and you do that 3 times in a row, it takes 3 seconds. I mean, that is just basic math, right? That's how time works.
Right, yeah, exactly.
But what if I told you there's this hidden mechanism inside modern software that actually allows a program to pause for 1 second, 3 separate times, and the total time that passes is just 1 single second? Welcome to the deep dive. Today, we're looking at how the digital world manages to basically bend time, or at least, create the illusion of infinite capacity.
It's a really phenomenal trick, honestly, because we all just expect our screens to load instantly, right? We're completely disconnected from the monumental traffic jams that are happening behind the scenes on the servers.
Oh, absolutely.
Like millions of people logging into multiplayer games or checking bank accounts at the exact same millisecond.
And our mission today is to demystify how that actually works. We're unpacking this concept called concurrent programming. We're going to look at how modern software handles thousands of tasks all at once without just melting your computer's processor.
Yeah, melting is a good word for it.
Right. And look, even if you aren't a software engineer, even if you've never written a single line of code in your life, stick with us. Because the mechanics of how we solve this problem, it offers a massive aha moment about how the internet actually scales to meet our endless demands.
It really does. It represents this fundamental shift in how we approach problem solving. It's not just about technology. I mean, it's about rethinking how we manage resources and how we manage time itself.
Totally. So we are pulling our insights today from a really engaging, narrative-driven article. It's titled The Secret Life of Python Introduction to Asyncio by technology writer Aaron Rose. And what makes this source stand out, actually, is that Rose skips all the dry textbook approach.
Oh, thank goodness.
I know, right? He sets a very specific scene instead. He places us inside this grand, quiet, Victorian library in London. So dark wood, dusty sunlight, the kind of place where true craftsmanship is revered.
Which is such a brilliant framing device, by the way, because it grounds these highly abstract, totally invisible computer science concepts in a physical, tangible space that you can actually picture.
Yeah, it helps so much. And in this library, we meet our 2 guides for the deep dive. There's Margaret, who is this brilliant senior software engineer, and Timothy, her junior colleague.
Right.
And when we first meet Timothy, he is in a state of absolute panic. He's built this custom chess club server, and overnight, it's just become wildly popular. He has 5,000 players trying to connect to his server at the exact same time just to check their match rankings.
Yeah, a good problem to have, but still a huge problem.
Exactly. But before we get to the magical time-bending solution that Margaret teaches him, we really need to understand why Timothy's computer is currently failing so spectacularly.
Well, Timothy has hit the classic scalability wall. Like, his server architecture worked perfectly fine for 10 people. It worked fine for 50 people. But the moment 5,000 concurrent users hit the system, the underlying foundation just entirely crumbled.
Okay, let's unpack this. Timothy's a programmer, so I'm assuming he's using a relatively modern laptop, right? He's probably got an 8-core processor, maybe 16 gigabytes of RAM, and 5,000 users just checking a chess ranking. That's just text. Text is tiny.
It is tiny, yeah.
So why wouldn't a modern computer just chew through 5,000 tiny text requests without even breaking a sweat?
Because of the approach he used to handle them, Timothy tried the most intuitive solution first. He used something called threads.
Threads, okay.
Yeah. You can think of a thread as like a virtual mini worker inside your application. He had 5,000 users, so he told the computer to spawn 5,000 virtual workers to handle them one-to-one.
I mean, that seems pretty logical. If you have 5,000 tasks, you hire 5,000 workers.
It seems logical until you look at the actual physical mechanics of what the computer has to do to maintain all those workers. Because virtual workers are not free.
Right.
Every single time a computer creates a thread, it has to carve out a specific chunk of physical memory, like a stack, just for that thread. Then, because the computer only has maybe 8 physical processor cores but 5,000 virtual workers, the processor has to constantly switch its attention between all of them. This is called context switching.
Wait, let me just visualize this context switching.
Right.
Is it like, say, having 5,000 open books on a desk and you're trying to read one sentence from each book, one right after the other?
That is a great way to look at it, actually, because to read a sentence from book number 400, The computer has to save its exact place in book 399.
Oh, wow.
Yeah, it puts book 399 down, picks up book 400, has to remember the context of what book 400 was even about, reads the sentence, and then it has to start the whole process over for book 401.
That sounds exhausting.
The administrative overhead is immense. Very quickly, the computer is spending like 90% of its processing power just organizing the workers and switching between them, and only 10% of its power actually doing the work.
So the management of the workers becomes way more exhausting than the work itself.
Exact.
That definitely explains why his laptop fans started screaming. But the text mentions he tried something else after threads failed. He tried processes. What is the difference there?
Well, if threads are workers sharing the same desk and constantly bumping elbows, processes are entirely separate, isolated environments. It's like building an entirely new, fully staffed restaurant right next door just to serve one additional customer.
Oh my gosh. That sounds expensive.
It is. They are incredibly stable because they don't share memory, so they don't trip over each other. But the memory cost is just astronomical. When Timothy tried to spawn 5,000 processes, his computer's memory completely ran out after just a few dozen connections. It crashed.
Okay, so the brute force method is a complete dead end. Adding more workers literally breaks the machine. But here's the piece I'm still trying to wrap my head around. What were those 5,000 workers actually doing that caused the crash in the first place?
And this is the real tragedy of Timothy's situation. Margaret actually points it out in the library. They were doing absolutely nothing.
Wait, nothing?
Nothing. In Timothy's code, a user connects, and then the server has to fetch their chess ranking from a database across the internet. Sending a request to a database and waiting for a response takes a few dozen milliseconds.
Which doesn't sound like a long time to us.
Right, but to a computer processor, which operates in nanoseconds, a few dozen milliseconds is an absolute eternity.
I see. So Timothy essentially hired 5,000 people to hold the telephone to their ear, stare blankly at the wall, and just wait for the database to ring back.
Exactly. You go completely bankrupt, paying the hourly wages of 5,000 workers before anyone even answers a single call. The virtual workers consume massive amounts of memory and CPU power just to stand around waiting for the network.
Wow. So if adding workers breaks the machine, and we still have 5,000 people waiting for their chess ranks, what is the alternative? Because we clearly need a completely different paradigm for how the computer manages its time.
We do. We need to stop equating handling multiple things with creating multiple workers. And this is exactly where Margaret provides a physical demonstration in the library that completely reframes the whole problem.
Yeah, she stands up right there in the middle of this quiet room, picks up 3 tennis balls, and just starts juggling. And she tells Timothy, you don't need 5,000 workers, you need one grand juggler.
It's the perfect metaphor for what Python calls Asyncio and this concept of the event loop. With Asyncio, we completely abandon the idea of hiring thousands of workers. We don't spawn thousands of threads. We don't build new processes.
Right.
We stay on a single thread on a single processor core. We just have one single worker.
Let me make sure I follow this. We were going from 5,000 workers down to just one. How on earth is one worker handling 5,000 chess players at the exact same time?
By never, ever waiting. The event loop is the grand juggler. When the juggler starts a task like fetching that chess player's ranking from the database, there is going to be that delay we talked about.
The eternity of milliseconds.
Exactly. In the old thread model, the worker would just stand there and stare at the database until the data came back. But the grand juggler, the absolute millisecond a task has to wait for anything, the juggler throws that ball into the air, looks away entirely, and immediately grabs the next task.
Here's where it gets really interesting. Let's move from the library to like a restaurant for a second to really lock this in.
Okay, I love a restaurant analogy.
So the old thread model is like hiring a different waiter for every single table. You have a waiter at table 5 who just stands there staring blankly at you while you slowly read the menu, and they're unable to do anything else.
Yeah.
But Asyncio, on the other hand, is like having one incredibly fast waiter for the entire restaurant.
Yes, your single waiter is the event loop.
But the waiter isn't literally pouring a drink at table 2 and handing a menu to table 3 at the exact same physical moment, right? They're just moving continuously. Instead of standing at your table waiting for you to read the menu, they walk away. They take a drink order at table 2, run food to table 3, drop a check off at table 4, and they come back to your table right at the exact millisecond you finally close the menu to order.
What's fascinating here is that that is precisely how it works. And to build on your restaurant analogy, the full waiter is utilizing the dead time or the waiting time of the customers to serve everyone else. The source text actually has an incredible quote from Margaret that sums this up beautifully. She tells Timothy that Asyncio doesn't do things at once. It waits for them at once.
It waits for them at once. Oh, wow.
Yeah.
That is the secret to the 3 seconds becoming 1 second that I mentioned at the very top of the deep dive.
It is. The single worker isn't moving faster, really. The worker is just overlapping the dead time. The juggler switches between tasks so rapidly and overlaps the waiting period so efficiently that from the perspective of the diners or, the chess players, it feels like they have a dedicated worker.
Because there's never a delay from their perspective.
Exactly. This is how a single server handles thousands of players without crashing.
Okay, the juggler metaphor makes total sense for a human being in a physical space. But, computers aren't humans, and they aren't physical jugglers. They are dumb machines that just read lines of text top to bottom. If I write pause or wait for the database in my code, how does the computer know to go do something else instead of just freezing the entire system like it normally would?
Well, that brings us to the syntax, like how we actually communicate this concept to the machine. Margaret gives Timothy a sort of cheat sheet for the vocabulary of Asyncio. Because to make this work, the programmer has to use specific magic words.
Magic words, I like that.
The first big one is the coroutine. In Python, if you define a function using the words async def, it becomes a coroutine. It's no longer just a standard top-to-bottom function. It has a superpower now. It can be paused and resumed.
It's like placing a bookmark in a book. You can close the book, go read another one, and then come back to the exact paragraph where you left off with all your previous context totally intact.
A perfect comparison. The second magic word is asyncio.run. This is the command used in modern Python to actually start the event loop in the first place.
So is that kind of like turning the key in the ignition?
Yeah, but it's more than just starting the engine, because just writing the command doesn't mean it's actually running in that asynchronous way. Asyncio.run is you physically handing the keys of the processor over to the event loop manager.
Ah, I see.
You are explicitly telling the manager to take control of the execution, look at all the available tasks, and start juggling. But the manager only knows when to juggle because of the most important magic word of all, which is await.
Await. Okay, so when I type await in my code, what am I actually telling the machine? Am I telling the waiter, hey, I need a minute to decide. You can go help someone else?
Yes, await is the yield point. It is you, the programmer, explicitly telling Python, hey, I am about to wait for the outside world, a database, a network request, a timer, whatever. I do not need the processor right now. Take the keys back, go do something else, and check back on me later.
That makes so much sense.
And this introduces a critical architectural concept called cooperative multitasking.
Cooperative. I mean, that implies there's a non-cooperative way computers usually do that.
There definitely is. Normally, your computer's operating system uses preemptive multitasking. Think of the operating system as a pretty ruthless dictator. It sits above all your programs, and it violently pauses them by force, ripping control away from one program to give it to another so that everything gets a turn.
Wow.
Yeah, it's effective, but as we discussed with context switching earlier, it's incredibly expensive and chaotic.
So Asyncio just strips away the dictator entirely.
Exactly. Asyncio operates entirely on an honor system among your code functions. The operating system isn't forcing your tasks to share time anymore. Your tasks have to willingly, cooperatively give up control using that await keyword. You have to be a good citizen. If one function is selfish, the whole system just collapses.
So what happens if a piece of code doesn't honor the system? Margaret gives Timothy a pretty stern warning about this in the library, doesn't she?
She really does. She warns him about the traditional time.sleep command. In regular programming, time.sleep just tells the code to pause. But in Asyncio, Margaret calls it a selfish sleep.
A selfish sleep.
Yeah, because it doesn't yield control. It doesn't tell the juggler to go do something else. It physically stops the juggler's hands while they're holding the ball.
Oh, man. So go back to our restaurant. If the waiter tells the customer to yield with an await, the waiter says, I'll be back in a minute, and goes to help other tables. But a selfish sleep is the waiter just standing frozen like a statue at your table for 60 seconds while the whole restaurant literally burns down around them.
That is exactly the physical reality of what a selfish sleep does to a server. The entire event loop just halts. No other chess players can connect. No databases are queried. Everything stops. You absolutely must use await Asyncio.sleep instead, which tells the juggler to keep the ball in the air and keep checking on other tasks while the timer counts down.
That is wild. It really sounds like the ultimate cheat code for programmers. You just sprinkle some async and await magic words in your code, you overlap your waiting times, and suddenly your server can handle thousands of users basically for free without crashing.
It does seem like magic, yeah.
But every powerful tool has a hidden weakness. If this is so efficient, why not use it for absolutely everything?
Because of the fundamental nature of the tasks themselves, Timothy gets a little overexcited by his new superpower, naturally. He sees how fast Asyncio handled all the network traffic, so he asks Margaret if he can use it for his grandmaster analysis, which is this feature that calculates incredibly complex predictive chess algorithms, and Margaret just firmly shuts him down.
Let me guess, it's because math doesn't involve waiting.
You've hit the nail on the head. The entire premise of the juggler is throwing balls into the air when they have to wait. I/O tasks, input-output tasks, like fetching data over a network or reading a file, those involve huge amounts of waiting. But heavy CPU math, there is no waiting.
Right.
The processor is actively calculating every single nanosecond. To do heavy math, the juggler has to physically hold on to that ball and stare at it until the calculation is completely done. They cannot throw it in the air.
So what does this all mean? Let's bring back our superstar waiter. If the waiter takes your order, and instead of just handing the ticket to the kitchen, the waiter suddenly decides to go into the kitchen and physically cook a highly complex 5-course meal themselves.
Yeah.
That's the heavy math, right?
Yes, and to make that truly accurate to how CPU math blocks an event loop, imagine the waiter isn't just in the kitchen cooking. Imagine they are physically barring the kitchen door so no one else can get in or out until that meal is perfectly plated.
Oh, wow. So the entire dining room freezes? Nobody can order? Nobody gets their checks. Nobody even gets a glass of water until that single calculation is totally finished.
This is why understanding the underlying mechanism, like the WHY and HIW, is just so vital. You can't just slap Asyncio on everything and hope for the best. If you force the event loop to do heavy math, every single other chess player's ranking will freeze. The whole server locks up.
That makes perfect sense.
And this leads to Margaret's concurrency toolbox summary, which is essentially the golden rule for when developers should use which tool.
Okay, let's lay out that toolbox for everyone, because this is the practical takeaway. How do we know when to use what?
If we connect this to the bigger picture, it breaks down into 3 distinct tools, each with a very specific purpose. First, you have threads. Threads are best for small waits, maybe a few background tasks where you don't want to restructure your whole code base, but you have to remember they cost you physical memory and overhead for every single thread you create.
Right, the 5,000 workers bumping elbows at the tiny desk.
Exactly. Second, you have processes. Processes are your heavy lifters. They're best for that heavy CPU math, the grandmaster analysis. They get their own isolated environment, but they cost massive amounts of memory and CPU usage to spin up.
The separate, expensive restaurants next door. And finally, the star of our show.
Asyncio. Asyncio is best for handling thousands of I/O waits. So thousands of network connections, massive amounts of database queries. It uses barely any memory, but the trade-off is that it requires strict single-threaded discipline.
You have to be cooperative.
You have to be a cooperative citizen, you have to use await, and you absolutely cannot block the juggler with heavy math or selfish sleeps.
It is just so satisfying to see how those pieces actually fit together. It's not about one tool being the absolute best piece of software ever made. It's about deeply understanding the nature of your specific problem. Are you trying to wait for 5,000 phone calls to ring? Or are you trying to calculate the orbital trajectory of a rocket? You need a completely different paradigm for each.
And that's exactly why Margaret and Timothy's conversation in the library is so illuminating. It takes this highly technical, often intimidating jargon like coroutines, event loops, cooperative multitasking, and it just grounds it in the physical reality of how a computer processor actually spends its time.
It really does. And, I want to tie this all back to you listening right now. Whether you are prepping for a software engineering meeting, whether you are trying to learn Python on your own, or if you are just insanely curious about how the internet functions under the hood, you now understand the invisible grand juggler.
You know the secret.
Yeah. You know the secret of how the apps you use every single day manage to keep running smoothly, handling millions of us at once, without instantly crashing the underlying servers. It's all about overlapping the dead time.
It is. And it leaves us with a rather profound final thought, too, based on Aaron Rose's article. When you really distill the mechanics of it, Asyncio achieves its incredible speed and efficiency not by doing more work and not by moving faster. It achieves scale by mastering the art of waiting.
Wow, mastering the art of waiting.
Yeah. It optimizes the pauses. It kind of forces us to ask a question about our own lives, right? When we feel completely overwhelmed by information and endless tasks, are we trying to use brute force to do everything at once?
Are we spinning up too many mental threads?
Exactly. Are we constantly context switching and burning out our own memory?
We try to be like Timothy's screaming laptop with 5,000 workers, exhausting ourselves just managing the panic.
Exactly. Or could we be more efficient and perhaps a lot calmer by simply learning to manage our waiting periods better? By recognizing when we are blocked, learning when to confidently put a task in the air, focus on the next immediate thing, and trust that the first task will come back down when it's ready, just like the Grand Juggler.
Optimizing the pause. I love that. Little Victorian library wisdom for our modern, hyper-connected lives. Thank you so much for joining us on this deep dive. Keep questioning how the digital world around you is built. Keep looking for the grand jugglers and the systems you use every day, and we will catch you next time.